Hi, everybody. My name is Ryan Marcus. I'm a new assistant professor at the University of Pennsylvania. Today, I'm going to talk to you about some of the work that we did in collaboration with TUM, Intel Labs, and Meta for implementing learned query optimizers inside of Presto. So I wanted to start out by giving the sort of higher level motivation for this work and this type of work. The claim that drives our lab at UPenn forward is the observation that hardware and application diversity are growing really fast. A kind of silly proxy for this is to go onto the Amazon EC2 product page and see how many different types of instances you can possibly pick from. In 2018, this was a reasonable number that you could maybe fit in your head. Now there are thousands and there's no possible hope. So in addition to hardware becoming more and more complex and more heterogeneous, applications are also becoming more and more complex and more heterogeneous. We want to do time series analysis, we want to do transactional workloads, we want to do analytic workloads, etc. Those two things are growing much faster than the number of people in this room who build systems to support those tasks. So this represents sort of an existential threat to data management. This is a really big problem where the general purpose systems that we built 20 to 30 years ago are now having trouble keeping up with new techniques. Our lab's proposal, and many other labs there as well are doing work in similar space, is to try to build systems that are instance optimized or that are learned systems. And the key idea behind these systems is that we want them to be able to do three things. First, we want them to automatically be able to invent new approaches to solving data management problems that the user has, possibly through program synthesis or through some other means. Second, we want these systems to be able to adapt to changes in the user's workload and to the user's hardware. And third, we want these systems to go beyond just a simple understanding of SQL and to actually understand what the user's intentions are, what their application is actually doing underneath the hood. Now, in classic academic fashion, I have overpromised. I will now underdeliver. Today, we're going to talk about the very first step that we took towards this vision inside of PrestoDB. I'll start out by giving at the risk of explaining something to people in this room who might know more about it than I do, a very high-level view of the Presto rule-based optimizer. I'll talk about kind of the troubles and difficulties you can encounter with a rule-based optimizer, and I'll give a brief overview of the system that we built, the open source system that we built with Intel and TUM called AutoSteer, which uses machine learning to try to figure out which rules to use in which situations. And then I'll show some experimental results from applying this to a real workload at Meta, and how we were able to achieve some improvements in tail latency. And finally, I'll go over some future directions and ways that we can possibly collaborate to make Presto even better. So I'll start out by giving a high-level overview of how the Presto rule-based optimizer works. The job of a query optimizer in any database system, including Presto, is to take some incoming query queue from the user, do a whole bunch of stuff to it, and output what is essentially a program that's going to effectively and correctly answer that query, hopefully not using too many resources and hopefully not needing too much time. Generally, the optimizer has to deal with a whole gigantic slew of problems. The three specific problems that Presto has to deal with are choosing a join order, figuring out, do I want to do T1, T2, or do I want to do T2, T1, figuring out how to distribute tasks over a large number of distributed machines, figuring out which operators to use where, hash join, merge join, etc. The reason that this problem is so difficult is that once you start having a reasonable number of joins, there are a whole lot of different query plans that you can pick from. So here we show a histogram for one particular query from the join order benchmark, or the JOB benchmark, where the number of query plans is on the x-axis, and the y-axis indicates how long those queries take to execute. So there are some plans, a very small number of plans, that are really good, that execute sometime between 1 second and 1 minute. And then there are some other query plans that are really bad that might take multiple days to execute. So the query optimizer's job is to take that incoming query queue and find one of the plans on the bottom part of this histogram instead of at the top part of the histogram. The way that the Presto optimizer works specifically is it's what's categorized as a rules-based query optimizer, which means that your initial query comes in, you turn that query into some kind of very basic logical structure or a very unoptimized form, and then you run it through a number of rules which will continue to optimize it. So for example, one rule that you might run your query through is a constant folding rule, which will make some kind of modifications to your query plan, shown on this little stick figure diagram as going from orange to a darker red. After you apply that rule, you might then apply a subquery rewriting rule that then makes more significant modifications, and you might pass that in to a join reordering rule that again makes some modifications and changes to your database. Now in modern Presto, there were, in 2020, there are way more now, there were about 50 of these rules, 50 different rules or stages that your query went through on its way from coming a SQL text to becoming an actual optimized thing. Now, obviously, I've admitted a ton of details here. Some of these queries run multiple times until they converge. Some of these rules only run in very specific scenarios, but overall, you can think about the Presto optimizer, at least in the context of this talk, as a pipeline of these rules that your query goes through on its march towards getting better and better and better performance. Rule-based optimizers are great because they have a high degree of simplicity and debuggability. You can look at an individual rule and you can say, is this doing a correct thing? Is this doing a good thing? But there can also be some problems that you can encounter inside of a rule-based optimizer. Ideally, every single rule in your pipeline will always improve performance for every single query that is applied to. But we live in data management land, which is the land of trade-offs, so occasionally some rules that are often good will go bad. So if today you decided that you wanted to take the Presto optimizer and implement a brand new rule called compress before transmit, which does what it sounds like, it says, okay, anytime that I have 3 nodes, n nodes needing to transmit all their data to one node, instead of just sending it, I'm going to have those nodes compress it first, here represented by the little compression symbol. So when you apply this rule, now when all of your nodes talk to one central node, they first compress that data initially. If you had not applied this rule, then that data would have been transmitted uncompressed. Now, as the designer of this rule, you might think, oh, well, this is really good because my data compression is going to work well because my particular network, is quite slow, or because I think that my data is somehow fundamentally very compressible. However, this same rule might be really, really bad when the cost of doing that compression or decompression is greater than the cost of just doing the transmission in the first place. So as a result, the exact trade-off of when your rule is a good rule and when your rule is a bad rule depends on the user's workload, how fundamentally compressible the data is. It depends on the hardware, how much network bandwidth you actually have. It can depend on the specific network conditions that you're working under. Maybe, Netflix is streaming its new special on your same cloud provider and now suddenly you don't have any network bandwidth, right? All of these things can combine together to make a rule like this very, very difficult to decide when should I apply this rule and when shouldn't I apply this rule. So with that background in mind, I can talk about AutoSteer. This is our machine learning powered rule selector. The fundamental premise behind AutoSteer is to try to say, okay, we have all of these rules. Wouldn't it be great if I had some kind of system that could automatically determine which rules I should turn on and which rules that I should turn off so I can get back to doing, my real job. So for one particular query, you might want to disable rule 2, but for another particular query, you might want to disable rule 1 and rule 4. Currently, we can do this today with tons and tons of manual experimentation, which if any of you have ever optimized a Presto query, you've probably done before. But the question we're going to look at today is, can we do this in a better and more automatic way? So the overall framework that AutoSteer uses is, first, we take a sample workload, a set of queries that are representative of what you want to do or what you want to execute. And for each of those given queries, we find the optimal set of rules to enable or disable. This is an expensive task. I'll talk about how we make it slightly less expensive in a second. After we do that, after we identify what is essentially a training set of good executions and bad executions, we aggregate all of that data together. So now we have examples of optimal hints and suboptimal hints for each one of those queries in the plan. Then we train a predictor. We use something called a tree convolutional neural network, but any ML model will do, in order to try to learn the mapping between, okay, for this query, I want to turn on this particular rule. For this query, I want to turn off this particular rule. For this audience today, I thought that the most interesting part to talk about would be about how we identify those optimal rules in a fashion that actually makes sense. I highly encourage you to check out our paper. I'll have a link up to it at the end that goes over the other 2 steps and how they were applied. But today, we'll primarily focus on, given a certain query, how do I find what the optimal set of rules are to enable or disable? Now, the first question you might ask is, well, this doesn't seem that hard. After all, the optimizer does it every single time you issue a query. But it's actually quite difficult to answer this question completely authoritatively. So if you have n rules and you assume that every rule can be enabled or disabled, which isn't quite true, some rules have to be on for correctness, some rules can only be on when other rules are on. But overall, in terms of big O, in terms of asymptotic behavior, we can assume that there's approximately 2 to the n possible configurations for any given query, where n is the number of rules that you have. In 2020, PrestoDB, again, now the number is larger, there are around 52 of these rules. Since a query can take a couple of minutes to execute, or possibly even much longer if your query optimizer does a bad job, this can be quite extreme. Believe it or not, I did run the numbers on this. 2 to the 52 minutes is too many minutes. I only have 6 years to get tenure, so that's not going to work out. So this is a major problem. And in fact, it's an even bigger problem now in current versions of Presto, where instead of having 52 possible rules, there are 170 possible rules that can potentially be on or not on. So how are we going to identify the optimal set of them, given that maybe I could have counted to 2 to the 52 at least, but I certainly can't count to 2 to the 170. Luckily for us, for any particular query, a lot of these rules are not active. They don't actually modify the query plan in any way. And we define an active versus an inactive rule. We say a rule is inactive if, when your query plan goes into it, you get the exact same thing out of it. And we define a rule as active as saying that when a query plan comes into it, you get something distinct out of it. We looked at a whole ton of queries at Meta and a whole ton of benchmark queries in TPCH and TPCDS, and we discovered that for the vast majority of, actually for no query used every single rule, which makes sense, and the median number of rules used was way less than 52. It was something around 18 or 20. So our first goal is to identify what those rules are. So we know we want to find the optimal set of rules. We're going to simplify that problem down by saying instead of finding the optimal set of rules, let's just find the active set of rules. And we're going to hope that that number k of rules that actually modified the query plan in some way is significantly smaller than n, which it does appear to be in actual data. Now, luckily, query planning is much faster than query execution, which is awesome, but we still can't test 2 to the 52 things because that's too many things. So what we can do instead is we can directly observe which rules changed or don't change a particular plan during optimization. And the way that we did this was with a very simple hack inside of the Presto code, where we checked the hash value of the plan before and after applying each rule. And if that hash value was was identical, then we assumed there was no change in the rule, and otherwise we assumed that there were. And this allows us for any given query to identify the approximately 20 active rules that are involved with that given query. So now we've reduced our problem from 2 to the 140th to 2 to the 52 to 2 to the 20. But unfortunately, even the naive solution here of executing those 2 to the 20 queries, it's still like 10 million query executions. If these are long-running queries touching petabytes of data, that's really not something that you want to do. So we need to continue to simplify the problem. And at this point, we make a very strong simplification in order to get some traction here. And that simplification that we make has to do with subplan optimality. So basically, if you imagine you have some original plan with all 4 of your query optimizer's rules enabled, and that original plan takes 70 seconds, suppose I then come and disable rule 1, and I observe, okay, with rule 1 disabled, my plan now takes 45 seconds. If, in my further experimentation, I try disabling R2, and I observe that R2 takes 90 seconds, I'm going to take these 3 pieces of information together, and I'm going to make a new assumption. Sorry. Should have done that a while ago. I'm going to make a new assumption that if I were to disable R1 and R2 at the same time, because R2 led to such a big slowdown, I'm now going to get something worse than when I just disabled R1. So this is a much weaker assumption than it might appear at first. So you might think at first, oh, they're assuming each one of these rules is independent. That's not exactly what we're assuming. Instead, what we're assuming is that if disabling one particular rule makes your query plan slower, then further disabling more rules cannot possibly lead you to a new optimal. In other words, we're assuming monotonicity of rules. If your rule helps improve your query plan in one particular instance or hurts your query plan in one particular instance, it will continue to help or hurt regardless of what is happening. And with this surprisingly, it's a moderately strong assumption, I'll admit, but it's not the strongest assumption in the world we could have made. We can solve this problem of identifying optimal rules using a simple dynamic programming scheme. You can take your original query, you can execute that original query, and you can observe how long that it took, and then you can try disabling each individual rule, and you can observe the new times that those took. After you make these observations, any rule that you disabled, which caused your query performance to increase, so in this case going from 70 seconds to 90 seconds, can be excluded. You know that you no longer need to consider possible rule configurations where R2 is disabled because of the assumption on the previous slide. But disabling R1 led to an improvement for this query, disabling R3 led to an improvement, and disabling R4 led to an improvement. So I now need to test the next level down, the next level of dependence, where I disable R1 and R3, R1 and R4, and R3 and R4. This has a surprisingly strong connection to your regular Salinger top-down, cost-based optimizing dynamic programming scheme. It's actually almost the exact same problem of finding this 2 to the n a thing inside of a permutation space. So this dynamic programming algorithm lets us very quickly identify that the optimal thing to do for this particular query is to disable R1 and to disable R4. Slides are out of order here. So once you have this thing, once you have this ability to take a query and instead of in 2 to the n possible executions and way, way fewer than that, in approximately n squared executions, determine what the optimal set is, you can take all of your queries in your sample workload or all the queries that you care to optimize, and you can figure out, okay, what's the optimal rule for each one of these? What are some examples of suboptimal rules for each one of these? And you can build a gigantic training set. Then you can take that gigantic training set and you can throw it into the machine learning model of the week, and lo and behold, you'll get some decent results. Our open source implementation of AutoSteer does exactly this with a machine learning model called a tree convolutional neural network. I'll have the link up to it at the end. It's very cool. It's almost amazing that it works. But there's another thing that you can do once you have this data set and once you have this particular algorithm, which I think is even more interesting for, even more immediately practical. And that is any time that you discover for a particular query that disabling a rule made that query faster, we can instead think, well, that's a performance bug, right? That is something that my query optimizer is doing, that instead of optimizing my query is de-optimizing my query, and whenever you have a component that is supposed to make X go up but makes X go down, we can call that a bug, right? The contract of the query optimizer should be rules make query go faster, we observe query not go faster, therefore bug. Great. Because of that, this becomes a very, very useful query profiling, query optimization tool, which we applied to a very large data set at Meta. So what we did here, what this experiment is showing, is showing an instance of AutoSteer. That is the blue bar. It's showing the best known plan that we were able to find at all. That's the algorithm that I just described to you in the orange. And it's showing PrestoDB default with all of the rules checked to on, which is what's in that red bar there. We're showing the percentiles here. So as you can see, the median query in this particular workload is quite fast, under a minute, but the tail is quite extreme, some queries taking up to an hour, et cetera. This is a dashboarding workload. There's approximately 1 million queries represented here. The data set size is greater than 3 petabytes. I'm not supposed to be more specific than that. So you can see that this machine learning model, which is represented by going from the orange bar to the blue bar, is quite good. It's able to drop the tail latency from 50 minutes for this particular workload to 37 minutes, which is really, really, really awesome. But there's actually more performance on the table than that. We should somehow be able to go from the 37 minutes of P99.9 latency down to just 32 minutes. And when we dug into this, when we used AutoSteer as a query profiling tool, we discovered that the massive difference in these P99 tail latencies is actually coming from a single rule. So excluding the folks in the front here, does anyone want to take a guess what that rule was? No, any guesses? Oh, you all are no fun. Yes. It's not join order. Join order was my guess as well. It is not the join order hints. Yep. So the actual hint that was causing the lion's share of the improvements that we saw with AutoSteer, or if you prefer the other interpretation, the lion's share of the bugs that we're observing here in the tail latency came from the hash generation optimizer. And I think it's important to understand the subtleties here, so I'm going to walk you through what exactly the hash generation rule does. So oftentimes when you're executing a distributed join, you get into a scenario where you have a whole bunch of nodes that need to broadcast all of their data to a single node so that single node can build a hash table or can have a hash table in the end. So one way to do that, the sort of default textbook way of doing that, is for node 1 to ship its values to node 3, the receiver node, for node 2 to ship its value to that receiver node, node 3, and then for node 3 to build the hash table, to compute the hash functions for each one of those items, and then build the hash table from it. This is a perfectly valid technique. It requires transmitting, in this case, 10 blocks of data, and then it requires computing 10 hash functions on a single node, in this case on node 3. What the hash generation rule observed is that this plan that I just showed you here lacks a degree of parallelism, because what I could have done instead is I could have gone on node 1 and said, okay, node 1, I want you to create all of the hashes right now for me ahead of time before you transmit to node 3. And okay, node 2, I want you to do the same thing. So now node 1 and node 2 have generated the hashes that they that would have, in the previous iteration, been generated on node 3. Then node 1 ships now 10 values, the original keys and the original hash functions, to node 3, and node 2 does the same. So now I've had to transmit 20 values. The amount of data that I have to transmit has doubled, but I was able to compute this hash function in parallel. Instead of having to transmit 10 values and compute 10 hash functions on one node, I instead transmitted 20 values, which is 2x, which is worse, but I was able to compute those 10 hash values in parallel across 2 different nodes. Now, the reason why the hash generation optimization might work or might not work can come down to a ton of different factors. The majority case that we observed at the meta workload was a hash join that was using a string as its join key, which is not really a situation you want to be in, but like you have to be able to support it because sometimes you have to do a hash join on string keys. And computing the hash functions of string values is a very expensive operation. You can try to do some cheat codes where you just hash like the first 4 characters of the string, which can speed things up quite a bit, but that can give you terrible skew and it can cause all kinds of other problems with collisions and stuff like that. So realistically, when you're doing joins on string types, you have to do this big nasty thing where you have order k, where k is the number of characters in your string, where you scan over all those different values. When you're doing that string join, the hash generation optimization is an amazing idea because the most expensive part of the procedure that you're executing is the actual computation of the hash function. So spreading that out in parallel over multiple nodes is a huge win that drastically overtakes the cost of having to transmit twice as much data. However, if you're using good old signed 32-bit integers for your data, then that hash generation parallelism technique doesn't work so well. And in fact, in a C++ implementation or in a naive Java implementation, the default hash function for an i32 value is just return x, right? It's just the identity function. So in fact, this parallelism gives you exactly nothing. You literally duplicate your data, and then you transmit twice as much data, which is extremely unhelpful. So sometimes, either when my network bandwidth is highly constrained, or when my hash function is especially cheap to compute, I want to turn off hash generation. But other times, when my network is highly constrained, which is the norm, or when I have these very weird join keys, which is admittedly not the norm, I want the hash generation rule to be on. And if you do this, the vast majority of this gain and tail latency can be fixed. And in fact, Preetava and Nikolai, the two other co-authors on this work, were able to take those 2 conditions and write up a heuristic from it after this work and actually implement this change inside of Meta's instance of Presto inside of these dashboarding applications. So the debugging in that sense was a success story. We identified the rule that was problematic and we were able to write a heuristic that worked. And we were able to achieve performance matching the yellow bar. But of course, that took a just absolute ton of effort, right? We had to do a whole bunch of work, a whole bunch of investigation, a whole bunch of looking into the nitty-gritty details about how each one of these rules worked, a whole bunch of modeling to understand why computing the hash functions of certain data types was expensive versus not expensive, a whole bunch of modeling to compare the cost of generating each hash value to the cost of transmitting that hash value over the network. And it was a great thing. It was a super fun project to do, and it's awesome that there are companies in the world that can employ people to dig down into that level of depth inside of their engines. Alternatively, if either you yourself or you have a customer that does not have that level of massive workforce capable of optimizing a particular Presto system, AutoSteer was able to automatically infer a large proportion of the time when to turn that hash generation on and off. Now, AutoSteer obviously didn't learn anything intuitive like what I just told you about, oh, if it's a string type, do this. If it's not a string type, do this. Or, oh, if the network is congested or not congested, et cetera, et cetera. It learned sort of a vague black box of amalgamation of different statistical facts that happened to be correct a lot of the time. But if you don't have those resources, or if your customers don't have the resources to do that level of deep diving into a particular Presto rule, the automatic learning procedure can capture the majority of the benefit with significantly less effort. So if that kind of thing sounds interesting to you, I highly encourage you to check out our paper, which is available at this QR code. I'll have the link up again at the very end of the talk. I apologize again for not covering all of the different ML components. I very rarely get to talk about the internal details of the query optimizer, so I was excited to do that. So please do check out the papers for additional details. Additionally, if you'd like to skip the paper and go right to the code, you can check out Intel Labs' open source implementation of the AutoSteer framework, which contains all the code that you need to find the optimal hint sets for your Presto queries, train machine learning models to automatically identify what those optimal hint sets are, and to deploy that model in inference mode in production on your cluster. And that code is written up, and you can take a look at it if that's something you're interested in. If you're interested in doing the deep level of exploration that the folks at Meta were able to do for this particular rule, we also created Christoph Anneser, the first author of this particular work and the PhD student who should be getting all the credit, created this super awesome tool called QO Insight, which allows you to compare query plan 1 to query plan 2 based on which rules you turn on or off, and then to analyze the performance in terms of network and cache misses and performance counters and all of that good stuff. So if you're interested in doing a deep dive or debugging a particular performance rule, I highly recommend you check out that work as well. And my final call to action to you, first of all, if you'd like a copy of these slides, they're available on the schedule website, but you can also get them from this link right here. And if you are interested in working on these types of query optimization problems that are hard, and you're looking for academic collaborators, please do come find me. Feel free to find me just at the reception or hit me up, email, Twitter, Mastodon, website, you know the drill. Happy to take any questions. Sorry.
Do you consider the correlation between the rules or dependency between the rules? Maybe turning off a rule may not be the same as you do it in isolation versus turning it off after applying a particular another rule with which it is correlated?
Yes, that is a great question. So a lot of the rules in Presto have been engineered to sort of assume that future rules are coming or that future rules have already executed. And this can manifest in two ways. One way that it manifests that's a serious problem for AutoSteer is that sometimes some rules for correctness assume that other rules are on or off. And now when you disable some rule earlier in the pipeline, suddenly this rule in the middle actually creates an invalid query. And that is a big problem. I didn't show the details of it here, but we have a way to essentially detect the point where a query becomes invalid inside of the pipeline and to bail out early and to go back. There's a deeper issue, which I think you're also talking about, which is sometimes running rule 1 slows down your query and running rule 2 slows down your query, but running rule 1 and rule 2 at the same time actually speed up your query because there's a synergistic effect that ends up working. Our dynamic programming algorithm will not discover that. In fact, it will assume that such conditions don't exist, but the machine learning algorithm that we train on the data set generated from that procedure can learn those facts. And in fact, we did see a couple of examples of correlated rules appearing in the training data that were learned by the model. However, that's not a guarantee. That's just the machine learning happened to work. It's equally feasible that the machine learning happens not to work. But yeah, currently the only hope that this system has for learning correlated rules that don't break the query is for the machine learning model to pick up on it. Yeah. Yep.
My question is, you didn't talk about overhead of training. Is there something where you can kind of have a budget and you get better or worse results depending on how much time you want to spend training these models?
Great question. So the question is, this talk didn't go over the cost of generating that training set or training those models, nor did it go over the cost of actually doing model inference at query time. And is there perhaps some way to have a sliding scale or an anytime optimization algorithm where you say, okay, today I don't have 8 hours to optimize this query, I have 10 minutes, what can you do? So let me answer the first question first. So this AutoSteer is definitely designed for an analytics environment where you're executing the same queries repetitively. In the Meta dashboarding case, these were literally the same query being executed over and over again each time the dashboard was being refreshed, which means that you can kind of, if you have some really, really long procedure that takes a super long amount of time to optimize a query, you can kind of amortize that cost out over all of the different queries that are repeating. We don't right now have a way to do an anytime algorithm like you suggested. One possible way to do that would be to try to see how well the machine learning algorithm performs with less and less training data. Whenever you see these training curves, you always see this sort of lying down hockey stick thing where your model does really, really poorly, it very quickly starts doing much better, and then it takes a very, very long time to kind of get that last 1%. So it's possible that if you stop training data collection earlier, when you get that first initial descent, you could save yourself a ton of time. We didn't specifically look into that because in our application it was like, yeah, we're going to execute this thing 1,000 times a week for the next 50 years, so go nuts. But yeah, that's definitely a concern.
I have a question. So, I think it's very good that you also analyze why insights from the model, then have you ever considered maybe to understand why they are different and then feed back this insight back to the learning model to make it even better?
Okay, that's a great point. So once our machine learning model learns something somewhat intuitive about the underlying data, once we understand, oh, the machine learning model recognizes this scenario where the default configuration is wrong, the machine learning model makes the correct prediction, can't we use that information, can we distill that information from the model somehow to make either our models better or to make our optimizers better? So I have a technically correct answer for you that's disappointing, and then a real answer. The technically correct answer that's disappointing is that you can do this, but it's a very manual process. So the folks at Meta who we worked at on this hash generation optimization did exactly this, right? They spent the time to figure out, wow, why is the model turning off hash generation? Oh, it's turning it off in this case, in this case, in this case. What do all those have in common? Oh, it's network conduction or it's data type size. And then they manually wrote that rule, right? So this is an improvement over just my query is slow, why? I think. Like, it's much better to be able to say, my query is slow, here's the thing that fixes it, now go figure out why, right? Now at least you have like a reproducer in a solution. But the more automatic thing that you're suggesting, where my model learns a particular pattern, can I extract that pattern, have a human go, yep, that pattern makes sense, and then encode that into my optimizer, I think is still uncharted territory. I think that would be very interesting to try to figure out. Yeah. Yeah, that's a great question. So there's sort of like a burden of proof-esque problem with like, well, if the model learns to correct something, can I now consider the problem solved, or do I need to figure out my original system had that bug in it and spend the time to go and actually figure it out? And I think this is sort of, a matter of taste is the wrong word, but opinions vary and opinions are very strong about which answer is potentially correct. Some folks are more than happy to have their machine learning model simply figure it out and not worry about it anymore. Other folks want to have a deeper understanding of the decisions that are being made about their data warehouse, and they want to kind of deeply understand it. They should be equivalent. It should be kind of the same thing in order to say this model solves a bug as it is to say this model chooses the correct set of rules. But I don't 100% know how to make that connection formally. Oh, yeah, that's a good question. So could one potential solution to this problem of identifying the fault at the model or the optimizer be saying, okay, well, one option you have is relying on the community to solve all of your problems and you just can complain on Stack Overflow and hope for the best? Or you can, even if you don't have the skills necessarily to dive into the Presto optimizer code and figure out what's going wrong, you can run this machine learning model to at least create a much better reproducer, to at least create a much clearer example of like, hey, my query is slow by default, but if I turn off this rule, suddenly it's faster. What's going on? At minimum, that's better for the community, right? But at best, I think that actually might be enough for a lot of people. They might just say, hey, my query's faster now. Cool. Yeah. That's a great question. So we know that the model learns patterns between query plans and the rules that we should turn on or off. So the model has some intuitive understanding of query plans. So instead of mapping the query plan to the rule that we should turn on and off and then rerunning the optimizer to generate a new plan, why can't we just map the plan to another plan, right? We already have plan in, why can't we have plan out? And I think that's a really interesting line of work. We experimented with it a little bit at Penn, and we got really fantastic results with, from an academic point of view, one teensy tiny problem, which is about 50% of the time you generate a plan that doesn't correctly answer your query, which is, very bad for an optimizer, but still quite academically interesting. So I think there's something there, and the missing piece is sort of the formal methods or the formal reasoning to be able to say, yes, this rewrite is valid, or no, this rewrite isn't. That's currently kind of out of reach for automatic reasoning systems, but I think if we could figure out how to do that, then we could potentially do almost, basically exactly what you suggest. Yeah. Sorry, inference cost and? Oh, sure. So Inference costs of the model kind of depend on the size of the model that you want to build. So we had to up our model size from what we used in the lab to work at Meta, and we ended up with a CPU-bound inference time of around 45 ms, which is quite high. We were able to, that was just like the raw PyTorch code. We were able to optimize that out with JIT and all that stuff and get it around 20 ms on CPU. On GPU, you know, with batches, it was much, much faster than that, but you know, that's not the scenario that you're in. And then figuring out what exactly to do next in that model is definitely an open question. I don't have the answer to that. I think there's lots of different possibilities to try to understand how those models can work better. Lots of possibilities to look at giant data warehouses that are executing billions of queries and try to figure out how to do semi-supervised or self-supervised work. But I don't know yet. You know. If you want to work on it, let me know. Yeah.
What does your plan look like? Like, can similar queries match to the same set of rules?
Yes, so the input to our model is the full Presto explain output. So like the entire physical plan that is going to be executed. And then the prediction of the model is how quickly or how slowly we think that plan is going to execute. So we run the optimizer many times with different rules enabled or disabled, and then we use this kind of predictive model as a cost function, and we say which one do we think is going to be best. So it is possible, so the answer to your question is no, assuming that the explain output of Presto actually uniquely identifies a plan. But of course, if there's some implementation detail, if there's some difference in what operator was chosen that isn't outputted into that representation, that's going to be invisible to the model. But basically, when you type explain format JSON, paste my query, whatever's in that output is what's an input to the model. And if it's not in that output, it's invisible. Yeah. Yeah.
Is it always faster than the default optimizer? And if so, like, what are the restrictions and using it by default?
That's a great question. So this is something that I spend a lot of time thinking about, trying to convince people to put untested machine learning black boxes inside of their mission critical systems, right? Can we make, okay, I know. Can we make this guarantee that it's always an improvement? And the answer is no, but if you think about it, you can't really make the guarantee of always improvement about any change to an optimizer, right? If you run analyze, you might have regressions because the statistics that you find might make you choose different plans. Similarly, if you implement a rule like the hash generation optimization, which seems, or the hypothetical compression rule I presented, that might pass all of your tests, but in actuality, there could be regressions later on. So the direct answer to your question, is it always better? No, but neither is any change to an optimizer, unfortunately. The best way that I've found so far, and I'm absolutely open to new ideas about how to evaluate these things, is to look at median and tail latency. Generally speaking, for most analytic workloads, if you can improve tail latency by 20%, it doesn't matter if you have a couple of regressions because those regressions aren't in the part that matter. All right, thanks. I think I'm out of time.